Welcome to the HEC-RAS Bridge Hydraulics webinar. I'm Kristy Riley. I'm the Division Chief of the Hydraulics Division at HEC. This week was supposed to be our HEC-RAS Users Group meeting, but unfortunately it got canceled due to travel restrictions. So instead we decided to do a series of webinars. So the first one was for HEC-RAS 2025. We have this one right now for RAS Bridge Hydraulics. And then we'll also have another one for stormwater pipes. I want to introduce our speakers today. We're going to have Dr. Alex Sanchez present. He has been with HEC-RAS, the RAS team, for the last 9 years. And prior to that, he spent 9 years at ERDIC in the Coastal Hydraulics Lab. And then also we have Cameron Ackerman, who has been with HEC for 29 years and officially with the RAS team for the last 27.
All right, thanks, Kristy. We've got about an hour set aside today to talk about 2D bridge modeling. So what we have planned today is the first part. We're going to talk about our simplified 2D bridge modeling approach. And then Alex will come in the second half and talk about the more computationally challenging detailed 2D bridge modeling approach that we have available in RAS. So the simplified 2D bridge modeling approach we've had in RAS now for, I don't know, 5 years. I can't remember when we first released it, but we adopted a practice based on 1D bridge hydraulics. So the 1D bridge hydraulics we've had in RAS, we've been using for the last 25 to 30 years, making improvements every day. And so we utilize capability to develop a robust set of family of rating curves for the bridge, and we use that where we can model both low flow, pressure flow, and then pressure flow with weir flow. So for the simplified 1D approach, we have a 1D bridge hydraulics layout, which hopefully you guys are familiar with from your years of RAS modeling experience, where you try and locate the bridge, and then you locate the cross-section upstream of the bridge and downstream of the bridge. Upstream of the bridge is cross-section 3, downstream of the bridge is cross-section 2. That's historically how we've spoken of it. And then RAS would automatically compute internal cross-sections to represent the bridge deck taking away area from the cross-sectional shape, and include things like piers and abutments. We then would develop a set of hydraulic tables or rating curves to develop a headwater tailwater relationship from the tailwater cross-section 2 up through BD through BU up to cross-section 3, and develop that head loss set of curves. And we refer to those as a family of curves. So when we talk about this bridge modeling approach, some of us talk about it, we use the term simplified modeling, but in the interface you'll see 1D family of rating curves. And so that family of rating curves, we're going to talk about those a little bit later about how we utilize them. But essentially, what happens is that for any tailwater at the bridge, given a flow, we'll compute the corresponding headwater. That ends up where we have a series of curves that represent any flow regime that we could have through the bridge. And it's essentially a lookup table that's very fast and easy to solve. So how do we lay this out in RAS? In RAS, a bridge is represented as a SA2D connection. And so once we have our mesh developed, we would go in and identify the location where we wanted to place a bridge, strike our 2D connection line, and then in the editor and RAS mapper, we can provide a name and then identify the structure type. We identify where we're going to put the structure, we identify the structure type. But if you've been using RAS, you know that faces are what control how water moves through the system, and we want to align those cell faces with flow. When we first lay out that 2D connection, RAS is going to try and snap faces to the structure, but if your cell faces are large and not parallel with the line, they're not going to be aligned properly. So what we're going to need to do is enforce that line to align the cell faces. Before we do that, we would go in and we would edit the 2D properties that are going to be used in the brake line for brake line use. And that's where we go in and we would set our cell size if we wanted to change the cell size from our nominal mesh spacing. And then we're often going to use this near repeats feature, which is going to the application of that break line upstream and downstream a number of times. So in this case, the example is 5. So when that gets applied, now you can see we've got cells that are aligned with flow 5 cells away. Again, you can specify that as many times as you like. You can add additional break lines, but this is the rudimentary first cut at it. At that time, we would exit out of RAS Mapper, and we would need to complete the data in the geometric data editor. So we'd go to the bridge editor, find the bridge of interest, and then we would need to add our deck and roadway. We're not going to go through the details of adding the deck and roadway. The details that are important here are that the width parameter that we specify is going to designate how wide our bridge deck is. And that's important because that's going to be used for identifying those cross sections BU and BD. Where should those be located? And then the distance parameter, which in 1D was the distance from cross section 3 to the next upstream cross section, that's actually going to be used to space the cross section from BU to cross section 3 and from BD to cross section 2. So where those bounding cross sections are going to go. Once you've entered that information, then you can go through and you can plot and see what your geometry is going to look like for each of those locations by working through the drop-down list on the plotter. So that's the basics to getting your bridge set up, is entering your bridge deck information and identifying where those cross sections are going to go. And then at that time, after that, you would go through all of the different editors. The first parameter, the one that we're concentrating on today, are just the bridge width and the distance parameters. And you'll see where those cross sections are going to be drawn based on your bridge. So here we see the bridge width being drawn based on that 40-foot size that we put in. And then those bounding cross sections of B, D, BU, and then cross section 2 and cross section 3. Based on those parameters. So RAS will draw those both in the geometric editor and in RAS Mapper if you turn on the plot option to do so. And those are automatically generated for you. Okay, so then as you work through the editors, the next 2 editors are piers and abutments. We're not going to concentrate on those today, but entering the piers and abutments will be included in the rating tables that we develop, the rating curves. The information, however, is not included in the mesh cell property tables. So the underlying 2D cell station elevation data will not be adjusted. That brings up the main limitation of using this process is because we don't have that information in the detailed cell property tables, they're not in the terrain, we won't be able to compute detailed velocities through the bridge. So if you have piers and they're going to greatly affect what the velocities are happening through there, you'll not be able to see those. And I'll demonstrate that near the end of the presentation. So if you want to have more detailed velocities, it's good practice to include the piers and abutments in the terrain. So you would include them both in the editor. So in this editor that you see here on the screen, we're entering our pier information so that they're included in the hydraulic tables for the bridge. But then we would also include them in the terrain so that when we went to go to the 2D computations, they would be included in the cell property tables. One thing that isn't obvious to users is when you enter the bridge information, we're creating those 4 cross sections that we've talked about. Cross section 3, BU, BD, and cross section 2. That station elevation information can be overridden. Not necessary to do it, and hopefully you don't need to. But what you do need to do is you do need to include the Manning's end value data for the bridge. So you'll have to go into the internal bridge cross section editor and add Manning's end values for each of those cross sections. And then the last piece of information we're going to talk about is entering hydraulic table parameters. That's how many points you want on your curves. These are the maximum values. The defaults will probably get you through most studies you're working on. So you won't have to enter the default information. What you will need to enter is the maximum head of water elevation. And all that does is limit the curves so that when you're computing them, we can get as much detail in the area of interest as possible. If you don't expect your bridge to be overtopped by more than 5 feet, then you just set this to be 5 feet over the top of the bridge. So once you've got your data entered, when you go to run RAS, it will pre-compute this family of bridge curves that we'll then use in our 2D solution. So the question you're asking is, how are we going to use that? So here's our 2D bridge curves, or our 1D bridge curves that we're using in 2D. And they are a representation of the head loss that is occurring from cross section 2 to cross section 3. For any tailwater, we can go in, follow that tailwater curve up to the flow of interest. Here it's about 18,000, and that will come across and give us our headwater. So here you can see we've got 1, 2, 2.5 feet of head loss due to the bridge. When we're solving the 2D solution then through the bridge, we'll see that the head loss might not match in the 2D solution. So what we'll do is we'll use a drag factor to adjust the friction loss for all the faces that are under the bridge. So the first example I showed you, we had big cells. We just had one cell. But in this case, maybe we have multiple cells. So what we'll do is we'll find out the head loss from this downstream cross-section to the upstream cross-section. Say it's 2.5 feet. We'll make sure that we have 2.5 feet of head loss across the structure. If we're not getting 2.5 feet of head loss across the structure from the 2D solution, we'll then use this drag factor to scale up the losses from each face as we move through the bridge. The drag factor that is used is constant for all faces. That doesn't mean we're going to get the exact same head loss from cell to cell, but we're going to be using the same drag factor. So this is an improvement that we made in 6.5, where we're using the bridge curves to compute a headwater based on a tailwater and flow. And we're applying this drag loss to all the cell faces under the bridge deck. So that has been occurring in version 6.5 and later. In previous versions, in 6.4, we did a little bit differently. We used the same curves, but rather than computing the headwater, we were computing the flow given the headwater and tailwater that the 2D engine came back with. And then in order to match that headwater tailwater, we were adjusting the flow using Manning's equation for only the cell faces that were directly under the bridge deck. And so that's why you'll see some of the examples we had larger cells, where in this other one, we could use smaller cells because we're applying the head loss drag factor to multiple cells through the bridge deck. What we found in the first implementation where we were trying to compute flow by adjusting Manning's roughness is that it was very sensitive to flow. It was not as stable, it was not as fast, it was not as robust. And so this new implementation in 6.5 is much more stable. And then in the latest release, version 6.7, the beta versions are out there right now. Beta 3 is our latest. The computational improvement we added was to improve the momentum equation for low flow through bridges. Historically, using the old momentum method that we were using, we were finding that it was very sensitive to cross-section shape and slope. So if you had a bridge where the slope changed rapidly through the bridge or just outside of the bridge, or if the cross-section shape changed just outside or through the bridge, what we were finding is that we would get these little hiccups in the hydraulic property tables for the bridge. And so because it was so sensitive, we'd get non-smooth curves, which obviously trying to interpolate or extrapolate on these curves, trying to find the correct solution, not nearly as stable as having nice smooth curves. So the new method, which is now the default method, we're calling the general method, it is more robust for natural channels. So that's kind of what's new from 6.4.1 to 6.5 to 6.7. Looking at the bridge output then, lots of different ways to look at the bridge output. We'll just touch on a little bit of it, not too far in depth, but you can bring up the 2D connection, look at the bridge, you can look at the table of curves, and then in blue, we'll show you the solution that was used during the simulation. So if you're having instability problems, right, when the water surface hits the deck or whatever, you can come in here and see, like, do I have a nice smooth solution? If not, where is my solution going unstable? You'll see a jagged line or a jump. And then if you want to follow it, when you animate, a little red dot will plot for you. It'll show you where you are for every time step. So it's a nice way to debug your model. If you want to do something a little more spatial, a little more visual, from RAS Mapper, you can plot bridges. And so Anton has added the ability to plot the bridge deck and then the headwater and tailwater water surfaces. We've also got the ability to use profile lines. So here I've got a profile line that is running longitudinal to my system. And so I can right click on that line or come over to the profile lines portion of the RAS Mapper view and look at mapping results, plot the profile, and plot the water surface. And then that longitudinal profile also will plot the bridge deck. That's a new addition. So you can see the water surface profile. Here we've got terrain, we've got the bridge deck, we've got the base profile with no bridge, and then we've got the profile with the bridge. All these things are animatable. So here you can see I'm dragging the slider bar, I'm animating the profile. It's showing me velocities in the channel while it's also plotting my water surface. If I want to know where I am at any point along this profile, you can scroll along it and you'll see over here, it's showing you where that location is along the profile line. And then the last little bit of bridge output, the latest thing that Dr. Sanchez has added is the ability to plot head loss through the bridge. So here you can see we can plot the head loss at any given time step through the bridge. You can see the drag factor that's being applied in order to get the head loss correct across all of the faces under the deck. And then an output of the error. And this error is what is the 2D solution getting versus what do the bridge curves predict that we should get. So obviously we want to have our error in the headwater as close to zero as possible. Oftentimes you'll see a spike, kind of like on the wetting front when the bridge deck might first get hit and the solution's trying to stabilize. But in the end, we want to have our error as low to zero as possible. This drag factor is just a knob to be applied to shear stress through the cells that are under the bridge deck. It's going to start at one being I don't need to apply any more losses, and then go up from there depending on how much head loss I've got through the bridge. Okay, so what's the limitation with this approach? We originally labeled this as a simplified 2D bridge modeling approach, and that's how we often talk about it. And it's simplified because what we're doing is we're taking this geometry and we're applying a tailwater and flow to get a headwater and developing a simple set of rating curves that we can look up later on the solution. What it doesn't do is it doesn't allow us to get detailed velocities through this cross section. It's great for coming up with a good water surface. It's going to be great for most modeling applications, but if you need detailed velocities through the bridge, you're not going to get them. And you can see that here through this example. As I turned on the bridge, this is just water depths, and then I turned on the velocity tracers. And you can see based on the velocity tracers, the engine doesn't know anything about what's going on underneath this bridge deck, as blocked out by these abutments. So I've got these abutments where I should not have any flow out here. RAS doesn't know that. The curves know about it, but the mapping engine and the 2D engine do not know about it because these faces, any faces that are under the bridge deck, the property tables are not modified for the 2D engine. So that's the limitation of this method, but I think it's robust enough for most modeling applications. If you need detailed bridge hydraulics, then you'll want to switch to the other approach that Alex Sanchez has been spending a great amount of time on, adding to RAS and improving.
Just to kind of clarify, 641 did modify the property tables using the bridge cross-section data. And then, because that one was only applying the losses at a single face at the center line of the bridge. But once we went to an approach where the deck could be multiple faces across, well, we couldn't override the property tables anymore because the geometry could be quite complicated because you have abutments and maybe multiple piers and such. And so we stopped overriding the terrain. And so if you want to see the piers and abutments represented in the 2D solution, then you have to put those in the terrain. So it's not required to put the piers and abutments in the 2D solution. You'll still get an answer that has the same head loss through the bridge, but it'll be a more accurate representation of the flow through the bridge because you'll see the flow go around the piers and it'll contract with the abutments and such. And so it's recommended to do that. So when we say detailed bridge modeling, it just, to me, it means high resolution modeling. And we've been able to do low flow detailed modeling forever. If you don't have the flow hitting the deck or overtopping the deck, you don't need to input the bridge, and you could just have a high resolution mesh and simulate the bridge hydraulics pretty well with RAS. But not being able to do pressurized flow and overtopping was a big limitation. And so for several years, I think about 4 years now, we've been working on this new feature, which is very innovative. No one else is simulating bridges this way. And we call it the pressure overtopping approach inside the UI. And it's basically a 2-layer approach, a 2D by 2, where we clone the mesh underneath the bridge and put another mesh on top of the bridge. And so you essentially have two meshes, one on top of the other. And we solve the governing equations, the shallow water equations in each one, and the flow can become pressurized underneath the bridge. So in this one, you do need the bridge geometry, obviously, but the advantage is that you can simulate all flow conditions, from low flows to highly submerged flows. It's the most physics-based approach that we have. And then we added the ability to simulate minor losses. So when flow goes around a pier, depending on the shape of the pier, you don't necessarily capture all the detailed hydrodynamics around the piers. So there's additional losses that occur there. Maybe the bridge deck has railings and a superstructure which also contribute to additional losses that aren't simulated in the simplified geometry that we're modeling. And also the scale that we're modeling, the cell size. And so we have a way of introducing additional losses in the model. And the other approach doesn't have this, right? The simplified 1D, 2D approach doesn't have this. You can combine these, or a part of your domain will be simplified 1D, 2D, and another part of the domain is pressure overtopping. I don't see that as being super common, but you can do that. When you put a bridge deck, shown here on the upper right, we clone the cells underneath the bridge deck and put them on top and create another mesh. We could have created a different mesh, but because we have the limitation where the user interface can't interact with this mesh, it's kind of generated at runtime. The simplest thing to do was to clone it. And these two meshes are only connected to each other at the edges of the bridge, obviously, right? You don't have flow going through the bridge deck. It only goes on and off the deck at the edges of the bridge. So that's shown here on the lower right. Okay, so I'm not going to talk about all the details of this, but the approach is very similar to how we do shallow water equations everywhere, except you'll notice that now there's a subscript L for the layer ID. And instead of the surface water elevation in like the pressure gradient term, now we have a hydraulic head, which has a water surface plus an additional pressure so that we can pressurize the flow underneath the deck. So that's the first layer, subscript 1 and subscript 2. The second layer is just the normal equations above the deck, and that's how we always compute the shallow water equations. But we do have this other, I mentioned the minor loss term, and that's what it looks like here. And then, of course, diffusion and bottom friction and all the other terms. One unique thing that we do in for the bridge hydraulics is that we simulate plunging flow. And this is what we call the flow conditions when the water surface on the downstream end of the deck goes below the crest of the deck. And obviously you have a flow coming off of the deck. We call that plunging flow. And in that case, it's more appropriate to solve an energy balance equation, and that's what we do. And then we have some methods for incorporating this into our discretization and final system of equations. And I won't get into all the details, but just know that this is part of it. And this is how we handle that difficult problem of plunging flow off of the bridge deck. Minor losses. So we borrowed this method from the two flow group. They use this slightly different in that they use this approach to capture all of the losses in a simplified kind of approach, like more like the 1D bridge curves and RAS. But we use it to capture all the little things that we don't capture with the geometry and the hydraulics. So we call it a minor head loss, right? And the total minor head loss coefficient has this shape. You have a constant value below the deck, and once you start hitting portions of the deck, then it starts increasing linearly, and you get to a maximum that's at about like 1.6 times the superstructure width, and then it's sort of kind of decays with elevation. And then in RAS, because we have 2-layer approach, we have to apportion that total loss coefficient to above and below the bridge, and this is the equation that we use. And this is all based on average velocity. So the minor losses that we apply, similar to that drag factor that Cam was talking about, we compute its value based on area average velocities, and then we apply that coefficient in a spatially constant way at all the faces underneath the bridge and above the bridge as well. And you have different values above and below the bridge. So this is from a paper that the two-flow group put out with the Queensland, basically Department of Transportation. It's called Department of Transport and Main Roads or something like that. And they use CFD modeling to come up with curves and values for this loss coefficient. Again, in their case, it's more of a total loss coefficient, whereas in our case, we're trying to just add the little losses that we're not capturing because our resolution is maybe too coarse, and we're not capturing the fine details of the hydrodynamics. The way you select this approach is very similar to what Cam showed for the simplified 1D, 2D bridge approach. And the structure type, if you go to an SA2D connection that has a bridge, you have the structure types. And this is the new approach, the pressurized overtopping method. So you select that. And when you select that, I'll jump to the other one. You'll see that the buttons on the left change, right? There's a lot more. There's the bridge curves. But if I select this one, then I only get two things. I get the bridge deck, the geometry of the bridge deck, and the 2D bridge parameters. This is where you enter the minor loss coefficients and the Manning's end for the bridge deck. And you'll also notice that a lot of stuff becomes grayed out here. If you're using this approach, you don't need to specify the Manning's end coefficient and all that stuff. And there's no like bridge method options either, right? Okay, so it's pretty simple. It's just geometry of the deck and those minor loss coefficients. So in the stuff that Cam talked about, the simplified approach, it's not critical that you enter the piers and abutments in the terrain. It's better if you do, the velocities will look better and the water surfaces, but in this approach, you absolutely have to do that, right, with vector mods. And only the deck is not included in the terrain, and obviously because we use a two-dimensional surface to capture the bathymetry. So now I'm going to talk about some subtleties and like how you set up the mesh for this 2D by 2 approach. As I said before, we clone the mesh that's underneath the bridge deck, which means it's kind of the user's responsibility to make sure that there are faces that line up with the bridge edge. And because we're cloning those cells, you have to be careful with adding refinement below the bridge for piers, because all of that resolution is going to be copied on top of the bridge, which may, reduce your time steps and cause instabilities and such. So that's kind of a limitation of requiring the same mesh below and above the bridge. So I often just stick to a simple mesh on top of the bridge, Cartesian or, quads above the bridge. In this approach, cross sections 2 and 3, which are shown by these dashed red lines, they're not used for the calculations, right? In the simplified approach, they get used to compute the curves. And this one, they're only used for output so that we can display the head loss through the bridge. Because you can show the same SA2D connection cross-section plot that Cam showed with this approach. However, the center line cross-section we do use for the computations because that's where we compute the area average velocities that get used for the minor losses, and then we apply those coefficients spatially uniform. Okay, and we also output variables along that cross-section, total flow below and above the bridge and things like that. You have to be careful how you place cells for the bridge. So coming from 1D, people are used to just making the bridge kind of expand the upper deck and then go along the roadways to and from the bridge super far, and it doesn't really matter for 1D. Well, that's what you do. For this, it does matter because everywhere where you put a bridge deck, you're cloning cells that are underneath. So in this case, on the lower right, basically you have a cell underneath the deck that has 0 volume. And then on the right, this got screwed up. The cell face should be here. You have a cell with a tiny volume right here. And as you know, time step is related to cell volume. And if you have tiny cell volumes, that is going to lead to instabilities and it may just blow up very quickly. You don't even know where it's happening. So best practice is to move the bridge deck from here to right here. And then this face, move it over from here to here so that you don't have that tiny cell volume. When you run the model, it'll show you that it has removed certain cells with the 0 or a small volume. And all the cell IDs correspond to the the lower mesh, right? It's not going to report any cell IDs to the upper mesh for the upper mesh. So more on mesh resolution, right? When you're doing detailed modeling, you start coarse and you refine. You should do grid convergence. From what I see users doing, the biggest issue people start having is they start with a super fine resolution model, and then they have slow time steps and they have instabilities. You should start coarse and let the model results guide you in where you put higher resolution. It'll go a lot faster. And you can nest the model, right? You can set up a coarser model, a bigger one, and then nest a higher resolution one by extracting boundary conditions at appropriate places from the larger model. That's very useful when you're doing detailed modeling. So diffusion wave, honestly, the only purpose for diffusion wave and detailed bridge modeling is for initial conditions or kind of preliminary runs where you're just trying to figure out kind of the extents of your domain, what areas are going to get wet and dry, what kind of resolution you need and such, or for initialization to create a hot start file. But all your production runs should be with shallow water equations, and specifically the ELM and EM. This image doesn't show it, but we also have a LIA approach, the local inertia approximation, that drops the advection and diffusion terms, and you don't want to use that one either. You want to use the ELM or EM, and I recommend EM for all your production runs because it has better momentum conservation, and because it doesn't do tracking, we can handle advection much simpler and more accurate from the first layer to the second layer and back. It's just it works much better. So turbulence also, if you're doing preliminary runs, you don't need to turn it on, but as you start kind of refining your model and start getting to a point where you're happy with it, turn it on. And I recommend the conservative approach for this. And actually, if you're using the EM solver, it's the only option, so you don't get to choose. And turbulence coefficients, especially if you have a lot of resolution in the model, it's important to at least do some sensitivity on the eddy viscosity parameters, or if you have data, calibrate. But if you don't have data, then do sensitivity analysis. Boundary conditions. Obviously, if you have a lot of resolution, it's very tempting to just put your boundary conditions as close as you can to the bridge deck, and then people will use a normal depth, which is not very accurate, and so you can end up with artificial backwater and things like that, or too low of a water surface near the bridge. So put your boundaries as far away as possible where you have data. And if you need to simulate a smaller domain because it's just too many cells, then do model nesting. Simulate the bigger domain, the coarse resolution, and then nest to get better boundary conditions. All right, and then for the mapping output, it's very similar to what you're used to for just regular 2D modeling, except now you have some additional output. The velocity stays the same, and it corresponds to the velocity in the first layer, right? But the water surface, it's the first layer by default, but once you have overtopping, it will switch to output the second layer water surfaces above the bridge. Because what people are generally interested in is how high is the water going to get, right? And they're not, if there's a gap in you know, if the water surface is at the bridge deck, they don't really care about that. They want to know about the water that's above the bridge and display that. So that's what we've done for the default water surface layer. That's right here. We do output 2 additional layers if you selected this method, which are above bridge water surface and above bridge velocity. Now, those data sets are only different at the bridge. Everywhere else, they're the same as they have the first layer results. And that's so that you can plot a nice smooth result, mapping result. So there's a lot of data duplication, but compression helps us there. It overrides the second layer results if the bridge is overtopping. If it's not overtopping, then you'll see that it's kind of dry, and it's just letting you know that the deck is dry. For profile plots, we have similar options to what the options that Cam showed for the simplified approach. You can make a profile line across the bridge deck, in the streamwise direction, and display like your water overtopping with velocity infill. That's this option down here. Or you can select the 2D connection plot, and that'll show you the kind of the bridge deck with the terrain and the water surfaces at those cross sections 2 and 4, which have the red dashed lines. Yeah, one note is, you need to put the bridge piers and abutments in the terrain. Now, the bridge piers, where do you end the bridge piers? Do you end them at the bottom of the deck, or do you continue them above? And what I recommend is continuing them above to the very top of the deck, the high chord, because when you display your results in RAS Mapper, it'll show at least that the flow going around those piers. Because if you don't, RAS Mapper doesn't know that there's a bridge deck there, and it'll once the water goes above this level, it'll seem like the water's going through the piers. So I make my piers such that they go all the way to the high chord of the deck. It just displays nicer in some cases. In other cases, like this one, it would look a little weird. It just depends on what you want for plotting, but the results will be the same. Now for time series plot, Cam showed that for simplified bridges, you get to look at the drag factor. Well, that doesn't exist here. We have different variables. And if you go to your bridge and then select options variables, you get this list here on the left. And so now you can look at variables above and below the deck, total flows, average velocities and such. You can look at the headwater, tailwater at those cross sections 2 and 3. And then you have all the minor loss stuff, the minor loss coefficient below and above the bridge, the total one, and then the minor head loss due to this extra contribution that you've added. So now I want to talk about some limitations, right? Obviously, this is, even though it's a 2D by 2 approach, it's better than having just one layer. It is still depth averaged, and we have a hydrostatic pressure approach. We do try to handle plunging flow in a more sophisticated and accurate way, but it is approximate. The high and low chords of the bridge are approximated with constant elevations. People know that RAS has subgrid technology, and if the terrain is varying underneath the cell, we capture that through these hydraulic property tables. Well, let's say your bridge is arching, we approximate that bottom of that arch as a constant elevation. And same with the deck, the high chord. If that surface is actually curved, we approximate it with a flat elevation. And for the top of the bridge is usually not an issue because they're pretty flat anyways. But for the bottom of the bridge, it can, it's an approximation. And it's just something that we had to do. Another limitation is that the user can't interact with the cloned mesh. You can't see the cell ID numbers and such. And so when we display at runtime, you get to see, if you go to max iterations and the error is above the tolerance, you get a little message that says you went to max iterations and your max error was this at this cell. Well, the way we show you that cell is with the ID number of the cell below the bridge deck. If that error occurred on top of the bridge, let's say, we show you the ID number of the cell underneath the bridge, and then we give you a little flag that says BR, indicating that it's actually the cell above that cell ID. And you don't know what that cell ID is. It's kind of created at runtime, but that's how you know the location. You know it's at this cell, but it's actually on top of the bridge deck. And there's other consequences of not being able to interact with this extra mesh, clone mesh. So we released this feature in 6.7 beta. We're now at beta 3. There are some limitations. We're still working on this, especially like the output and some improving stability and runtimes. We're still working on all those things. And the things that we plan to support by the official release of 6.7 scheduled at the end of the fiscal year is precip, evap, infiltration, wind, atmospheric pressure, and waves. At the moment, wind is the only one of those that is supported. I know that works well. Precip, for example, will just like go through the bridge deck and will be applied, under the deck. Is that a big deal? Not really, but we're gonna improve that, right? But the things that we just don't have time and funding to support in 6.7 and are not going to be supported are bridge openings such as culverts and things like that, and then combining this approach with other features in RAS, specifically 2D sediment, secondary flow, which will be new to 6.7, and so we haven't had time to merge those two things, debris flow, and I'm sure there's other things that I'm not thinking about. But most of the functionality will be there. I think the things that people care about the most are maybe precip and wind for this. So we have these two approaches. When do you apply either, right? Well, the simplified bridge approach, you should apply when you have a coarse model and you only care about capturing the head loss through the bridge. You're not interested in the detailed hydraulics through the bridge. But if you're doing a bridge design, or you actually want to simulate the hydraulics in very detail, then you need to use this other approach, especially if you have pressure overtopping. Okay, that's the main takeaway, right? That it depends on the objectives of your study, whether you just care about capturing the head loss because you're interested in flooding somewhere else, or if you're interested in the detailed hydraulics of the bridge, then you switch to one or the other.